All right, hello class. Since I'll be out this Friday because I'm going to do a recorded lecture, we got an exam coming up next Friday. I thought we should at least continue covering content. So I'm going to deliver today's lecture since we're out for a snow day. I will deliver this lecture through a video. And so the first thing I want to do real quick is just cover a little bit about electric dipoles. I moved your homework due date to tonight because your last question asks you about electric dipoles. So I want to first just explain what this is, and then I'll work a quick example. Real quick, an electric dipole is a condition where two equal but opposite charges are separated by a distance. Okay, and an electric dipole is quantified with what's called a dipole moment, and that's given by the letter P here. And P is simply the charge times the distance that separates it. Technically, the dipole moment, electric dipole, points in the direction from positive to negative, because this is the direction for the displacement vector. We're just going to be dealing with magnitudes, so you won't need to worry too much with the fact that it points from negative to positive. If you're familiar with chemistry, the convention in chemistry is that the dipole moment always points from positive charges to negative charges, so it's a little bit different. What happens for an electric dipole? If it's in the presence of a field, the negative charge wants to go upfield, and the positive charge wants to go downfield. And so this generates a torque on the dipole, and this is simply the cross product of the the dipole times, or the cross product of the dipole and the electric field, right? So that means that the maximum torque is experienced when the dipole is oriented perpendicularly to the field. This is where the maximum torque is going to be experienced, because the cross product gives you this is the sine of the angle between the two vectors. And so here the sine of the angle between the dipole vector and the electric field vector is 90 degrees. And then it's, of course, at a minimum when they are aligned, okay? And this can be aligned or misaligned. If it's misaligned, in other words, you've got this kind of orientation right here where the positive charge is downfield and the negative charge is upfield. There's no torque on this dipole, even though the positive charge wants to go this way and the negative charge wants to go that way, because the forces are equal but opposite. This is what we might call an unsteady equilibrium, because any small change in this would cause it to align with the electric field. So that's torque. Interestingly, if you put a dipole, and this is in any electric field, it'll experience a torque like this. If the electric field is not constant, then the dipole will, in addition, experience a net force that moves it in the direction of the stronger field. All right? And the reason for this is because, let's just say that here you've got an electric field that is stronger over here. So the electric field over here is strong, and then over here it's weak, because that's how the field strength is moving. Okay, so in that case, the negative charge is going to feel a force that wants to move it in this direction, and the positive charge is going to experience a force that wants to move it in this direction. And the negative charge, since it's in a stronger field, it will experience a larger net force than the positive charge. And so the overall force, the net force on the dipole, is going to be to the stronger part of the field. Now, you're not going to do really any computational work with this, but I want to make sure you qualitatively understood what happens to a dipole in an electric field. So just to summarize, a dipole in an electric field experiences a torque if it is misaligned with the electric field until it is aligned with the electric field. Now, if it's exactly opposite, that's the unsteady equilibrium case. Okay, and then if the electric field is constant, then it just sits there. But if the electric field strength is changing, then it's going to move toward the stronger electric field, right? So if it's stronger in this direction, it's going to experience a net force in that direction, and vice versa. Okay. All right, so this is a vector quantity, the dipole moment. And so you're going to need to be able to calculate the electric dipole, and the example that's given in the next slide will help us with that. All right, so let's take a look at this example to see how we can calculate dipoles. All right, so we want to, in this example, find the bond angle of ozone. That's this molecule right here. Don't worry if you're not a if you don't know any chemistry. Everything is in the problem statement. So this is just a geometric problem that we're going to use. Okay, so we're going to find the bond angle of ozone given that the central oxygen has a charge of 0.17 E, and the other two oxygens have charges of, and this should be a negative. These are both negative. 0.17 E over 2. The dipole moment is this. It's in coulombs meters. And the bond lengths are each that distance. All right, so let's just kind of highlight what we're looking for. We're looking for this bond angle that's labeled here, theta. Okay, we want to know what that is. And then let's just go ahead and label out everything. Let's label the charges. This oxygen, which is the central oxygen, it's in the middle. It has a charge of 0.17 E. And then these two each have charges of negative 0.17 E over 2. So there's all the charges. And then the distance, each of these bond lengths are 1.278 times 10 to the minus 10 meters. So that's this distance right here. Okay, and so what we want to do is solve for this angle. So let's first, real quick, we're looking for adding. We have two bonds. We have that one and this one. So we have essentially two electric dipoles that we have to add together. We have this electric dipole and we have this electric dipole. All right. So let's just illustrate both of those dipoles. And we're going to illustrate the vector problem down here. This is the central oxygen, and there are two dipoles. One of them is in this direction. We'll call this P1. And the other is in this direction. This is P2, all right? And these are separated by the unknown, which is the angle theta. Okay, and so what we want to do is add these two together. All right, now let's establish a coordinate system. We'll establish a coordinate system that this is, say, y, and this is x. And so when we want to add these two vectors together, we have to break them into their y pieces and their x pieces. Okay. And this, the coordinate system that we have chosen bisects this angle so that the y-axis bisects the bond angle. All right. So so these are the two vectors, and remember, the convention is that the electric dipole points from negative to positive, so that's in this direction, which is P1, and then in this direction, which is P2. All right. So now this is an illustration of the vector problem that we need to solve. Okay, and so then if we continue down here with this axis, we'll see that over here on the right, this is theta over 2, and this is theta over 2. Those two angles right there, because this bisects that. All right, so let's continue on. Let's add these together. Okay, so P1, I need to find the x and the y components of that. And hopefully you see that these are mirror images of each other. So whenever I find the x components, the x component of P1 is going to be based on the sine of this angle. So we'll call that P1x. Okay, and this is going to be equal to P1 times the sine of theta over 2. Okay, and then P2x is going to be equal to negative P2 times the sine of theta over 2. And since these have the same magnitude, right, both of these are have the same charges, then this is going to cancel out. So when I add these together, Px is equal to 0. All right, so then all we need to do is look in the y direction. So let's do that now. In the y direction, they're both pointed in the positive y direction. So then I'm going to have the overall y direction is the sum of both of those. So I'm going to have two of these terms from P1x and P2x that both add up to give me the total electric dipole. So whenever I add these together, we can recall that these have the same magnitude. Okay, so I'm going to have Py is going to be equal to P1y plus P2y, which equals 2 P1y, because they're equal, and I can just take the sum of them. All right, so let's go ahead and put in the values. Remember that the dipole is equal to Q times D. All right, and so that's what the P is. So this is going to be 2 times P times the cosine of theta over 2. All right, because that's the y component of P. All right, cosine is the adjacent. All right, so now we've got, and this is equal to the total dipole moment because there's nothing in the x direction. So that makes that a little bit easier. This is the dipole moment right here. Because that's the total dipole moment. All right, so now we need to substitute in for P for each one of these. Okay, so we have P. Oh, here let's call this P1 because they're the same. All right, so then P1 is equal to Q1 D1. What is Q? All right, so we look back here. Now we notice that this central oxygen has twice the charge as either one of these. So we can model this as two different dipoles where this one has negative 0.17 E over 2 and positive 0.17 E over 2. And this one is the same. It's negative 0.17 E over 2 and positive 0.17 E over 2. So that the total charge here in the middle is 0.17 E, where E is the charge of an electron. Okay, so we'll go back up here. We're going to plug in what Q is. Q is 0.17 E over 2. That's Q. And then D is the bond length. So that's 1.278 E minus 10 meters. Okay. So that is just the strength of the dipole of one of these. It's this term right here. Okay, and then what we're looking for is theta. So we can solve, at this point, we can plug in most everything that we have. We've got 1.77 E minus 30 coulombs times meters. This is going to equal 2 times 0.17 E over 2 times 1.278 E minus 10 meters times the cosine of theta over 2. Okay. And now the only thing we don't know is theta over 2. E is the charge, the elementary charge. And so we've got that. It's in our calculator. If you crunch through this, these numbers, I got theta is 117 degrees, I think. Here, let's punch through it real quick. Okay, so we're going to take 1.77 E minus 30. Okay, these twos cancel. Divided by 0.17, and then I need to divide it by E. So I'm going to go with my constants, scroll down to the electron charge, and then I need to divide that by 1.278 E minus 10. And then this gives me the cosine of theta over 2 is equal to 0.5085. And then I can use the arc cosine to solve for theta. So I'm going to use the arc cosine of the answer. And this gives me theta over 2, so I got to multiply by 2, and that gives me 119. So that's the bond angle for ozone. Okay, there's an example. You got something similar to this in your homework, so head there for practice. All right, on to the next chapter. We're going to go ahead. We're going to cover Gauss's law in this the rest of today's lecture. And Gauss's law is relatively simple. However, I do need to cover a little bit about electric flux, what it is, and what we can do with it. All right. So first, just in general, a flux is a measure of how much of something passes through a given area. Okay. So you can think about this in terms of like sunlight, how much sunlight is passing through a given area. You can think about it in terms of wind. So if you've got wind, how much air is passing through a given area. So that's just in general what flux is. And electric flux is defined as the amount of electric field that passes through a given area. Okay, so if you have just some arbitrary area, like some kind of window, for example, and you want to know how much electric flux is passing through that, then we would illustrate it like this. These are the electric field lines that we can draw going through that window. And in order to calculate this, it's an integral of the electric field, the dot product of the electric field and the area vector. Okay, so so this is simple when the electric field vector and the area vectors are perpendicular, and that's because it's zero, because when you have a dot product like that, it's zero. So this is the case where, for example, like this electric field right here, I want to lay my surface down on its side so that the electric field essentially passes like it's parallel to the plane of the area. And this is the case where the area vector and the electric field vectors are perpendicular. Okay, so just as a reminder, the dot product, for the dot product, this means that we take the cosine of the angle that separates the two vectors. Okay. All right, so let me explain real quick what this n term is. This is the direction for the area vector. Okay. The area vector points perpendicular to the area. So in this case right here, the area vector would point perpendicular to the area. In this case, the area vector points perpendicular to the plane of the area. Okay, so this is this n hat that's illustrated here, n hat. All right, and this is kind of weird, I know, but it's just the convention. Okay, so these the area vector points perpendicular to the surface instead of parallel to the surface, okay, the plane of the surface. All right, but the important thing, like if we understand the conceptual nature of this, then it becomes a little bit easier to kind of see how the math works. All right, so this is going to be a maximum when the plane of the area is perpendicular to the electric field, or the electric field and the area vectors are aligned. Okay, so let's make sure that we understand that. The plane of the surface is perpendicular to the area vector. Okay, so so make sure that you're paying attention to what angles and everything that's being illustrated in the problem. Okay. All right, so this integral might be a little bit scary. In fact, it is kind of scary when the electric field is not constant. But for pretty much everything we're going to do, the electric field is going to be constant over this integration. So with any constant, we can just pull it out. So that'll be nice. And then the integral just gives you the surface area. Okay. And that's when the electric field is constant, both in magnitude and the dot products is always, the cosine is always 0. Okay. Or 90 degrees. Okay, so this is in general what electric flux is. Okay, another convention that you need to be familiar with is that for an enclosed surface, an enclosed volume, the area vector always points outward. All right, so this is an important convention. if it's not enclosed, like up here where I illustrated this, I could have, with equal validity, pointed this to the left instead of to the right. Or this one I could have pointed down instead of up. All right. So if we're dealing with an enclosed volume, however, the convention is that the area vector points outward across the whole surface. Okay. All right, let's see how this works. All right. So we've got a uniform electric field, and we want to know what is the electric flux through a rectangle with sides A and B. Okay, side lengths are A and B. And we have two cases. One where this surface is in the XY plane and the other where it's in the XZ plane. Okay, so what is illustrated here is where this surface resides in the XY plane. Okay. All right, so then the area vector points perpendicular to the surface of the plane. So we can illustrate that like this. This is the area vector, which we illustrate with the area times the direction. This should be a little hat. The unit vector in that direction. Okay, and so then let's write down our equation. We've got the flux is equal to the integral of the dot product of E dA. Okay. All right, so E is constant, and the dot product of this, if we look at this problem, okay, for part A, the angle between the area vector and the electric field vector is 0 degrees. Okay, so if I explicitly write out what this is going to be, it is the flux is equal to the integral of E0 times the cosine of theta dA, where now this dot product is taken care of by the cosine. The angle between the area vector, this blue arrow, and the electric field is 0. So the cosine of 0 is 1. Electric field is constant. So I can pull it out of the integral. Well, and now I've just got the integral of dA, which is just the surface area. Well, the surface area of a rectangle is the length times the width. So that's going to be A times B. And this is the flux through that rectangle in the XY plane. All right, let's do the XZ plane. So in the XZ plane, we're essentially moving this box so that it is here like that. Okay. So the area vector, let me illustrate this with a red. The area vector points in this direction out this way. Okay, so in this case, the angle between the electric field vector, let me illustrate that here. Here's the electric field vector. And this angle is 90 degrees. Okay. So then when we come back to calculate the electric field, or the flux, this is going to be the cosine of 90 degrees. So whenever I put that in, this is 0. If that's 0, then it doesn't matter what the integral is, how complicated it is. It doesn't matter because 0 times anything is 0. So then I get 0. All right, so this next one, I want you to try this one. And just as a reminder, let me just go back. For an enclosed volume, the area vector points outward everywhere. Okay, so Here you're asked flux of a uniform electric field through a closed surface. Okay, so here's the closed surface, is this cube. Constant electric field of magnitude E0 points in the direction of the positive z-axis, so it points up. What is the net electric flux through a cube? Okay, so you have 1, 2, 3, 4, 5, 6 different surfaces that you have to calculate the electric flux through and add all of those up. Once you pause the video and then and try this out. Okay, so if you've gotten stuck and you've just hit play or you never paused it, let me get you started on this, and you can of course pause it at any point to try to finish the problem. Okay. All right, so here we've got 6 surfaces. Let's do all the side surfaces first because those I think are the easiest. So if I just take like this side over here, B, C, G, H, right there, the area vector points in this direction. Okay, so the electric field vector points straight up like this, which is at 90 degrees. So the flux through this surface on the side is 0. Well, this is also true for the other side and this one and the back one, right? So all 4 of those sides that are vertically aligned, those all have a flux of 0. So the flux for a side is 0. So this makes life a little bit easier. So all we need to do is look at the top and the bottom surfaces. So let's go ahead and do that. All right, so for the top surface, I'm going to draw the area vector. Here's the area vector. Direction. It points outward. Remember, for an enclosed volume, it always points outward. And then for the bottom, there's the direction of the area vector. Okay, so then let's go ahead and calculate the flux for the top surface. Okay, so on the top, I'm going to have the integral of E0 cosine theta dA. All right, and so then the cosine, the angle is 0, so cosine is 1. So this is going to be equal to E0 times whatever this area is. Let's just call it A. Okay. All right, and then let's do the bottom. So the bottom, it's the same thing. Okay, except what do you notice about the angle between the area vector and the electric field? Here's the electric field vector. This angle right here is 180 degrees. All right, so then I'm going to have the cosine of, in this case, 180 degrees. In this case over here, it was 0 degrees. Well, the cosine of 180 degrees is -1. So for the bottom, I'm going to have negative E0A because the surface area, the top and the bottom are the same. And so then I total, or I net, is equal to E0A minus E0A plus, there's 4 sides with 0. We'll go ahead and write that out. And this equals 0. Okay. Now, let's just conceptualize this real quick. Does this make sense, that the net electric flux is 0? Well, all the electric field that's going into the box is leaving the box, right? So if you just kind of think about this as like, let's just say this is a glass cube, right? And we have sunlight coming into it. Well, how much sunlight is going in versus going out? Well, all that's going in is going out. It's passing through it. So this makes conceptual sense with the concept of, net electric flux if we think about something like light, for example, or if you had some sort of cube out in space, in the atmosphere that wind could go through, then all the wind that went in one side would go out the other side. And so you can think about it in either of those cases. Okay, so the title of this chapter is all about Gauss's law. And Gauss's law, simply stated, is for an enclosed surface, the flux through that surface is Q over epsilon naught, where epsilon naught is the permittivity of free space. I want to show this derivation using a single positive charge with spherical symmetry, and then we'll take a look at a couple of really quick examples because Gauss's law is fairly simple once we kind of understand what it is telling us. Now, this is importantly for an enclosed surface. So that is a surface that completely encloses a region of space. It can't just be sort of an open box. It has to enclose a surface. Okay, so if we take a single positive charge and we want to look at this at some radius. This is going to be, imagine that's a perfect sphere. All right. And we know that the electric field lines point straight out like this. And they point away from the positive charge like so. All right, so these are the electric field lines. Now, technically, there's, we could draw more, but this is sufficient. And the area vectors all point, since this is an enclosed surface, they all point out. And they point out and they're perpendicular to the surface. So this would be the direction of the area vector at that location. Here, this would be the direction at this location, and so on, like that. All right, now when we illustrate that, hopefully you can see that the angle between the electric field and the area vector at each one of these places, all along this surface, is going to be 0. So theta is 0 here, theta is 0 here, theta is 0 all over this surface. And the reason for that is because we chose a sphere and the electric field has spherical symmetry around it. Okay, so now that we've gotten those two pieces of information, then we can move on to calculating the flux. So let's write that here. The flux is going to be the integral of E. And then I'm going to, instead of putting the dot in here, I'm going to put the cosine of theta and then dA. All right, so that's the dot product between these two is the cosine. All right. Now, the electric field is constant given that the radius of this is constant. All right, so we're going to have some radius that we'll just call R, capital R. All right, and the electric field out at this radial position, the electric field, because this is a point charge, is 1 over 2 pi epsilon naught Q over R squared, right? And if we want to refer to this as the vector, then we would do something like this, right? It looks like that. But we already accounted for the direction of the vectors and the fact that the angle between these is 0, and so all we need here is magnitude. All we need there is magnitude. Okay, so this is the electric field, and then I'm going to go ahead and plug that in, and recall that the cosine is 0 everywhere, so I can pull this is just 1, and then we're going to shove in what the electric field value is, which is 1 over 2 pi epsilon naught q over r squared integral of dA. All right. So this is the integral that we need to solve, and the area that we're solving for is the area of this sphere. And so then when you integrate over the surface of a sphere, the area is 4 pi r squared. Yes, 4 pi r squared. Oh, I'm sorry. This is 4 pi, not 2 pi. That's 4 pi epsilon naught. Okay, so then if we go ahead and plug that in, this integral is 4 pi r squared. So a lot of this stuff cancels. My 4 pi's cancel. My r squareds cancel. And I'm left with q over epsilon naught, which is what we get for an enclosed surface. All right, now we did this with a nice spherical symmetry. That made the math easy. The interesting thing about this is that even if you have a non-spherical surface, it's something like this. I don't know, something awful like that, right? The net flux is still the same for an enclosed surface, okay? Now, let's just, instead, we're not going to try to prove this. Let's just think conceptually about this. All of the electric field from this positive charge is going out of the surface, all of it. And then all of this electric field is going out of that surface. So the same amount of electric field is going out of the surfaces. So it doesn't matter like how convoluted this surface is. And you can even imagine that this area right here, if we sort of charted this out, where this is my electric field line, right? So this part of the surface right here doesn't really count for anything because it's all parallel, and then you've got this other surface that counts more or less, and so on. So even though the surface area of this is greater, when you do the dot product, if you were to work through the awful math that you'd have to do to solve this, you would wind up with the same answer. Okay, so this is for a single positive charge. This can be extended to multiple charges, where if I have now, say, a negative charge in here, and let's put another negative charge in there, and then I have electric field lines that are coming toward the negative charges and leaving the positive charges, leaving the positive charge, right? The overall, this is Gauss's law in a nutshell, the overall flux for this case is the net charge over epsilon naught. Okay, now so far we haven't worried too much. We've always put magnitudes of charges in here, but we need to include the sign here. The reason is, if you have a net positive charge, then the flux is going to be net outward. If you have a net negative charge, like is in this case where I have 1 positive charges and 2 negative charges, then the flux is going to be inward. The net flux is going to be inward. Okay, so we do need to account for the signs with these charges, and so let's just take a look at a quick example. So this is relatively simple, but let's go ahead and work through it. All right, so here I want to know what is the flux through surface S. Here's the surface right here. It's that sort of gray spot right there. And then the flux is going to be equal to the net charge. Okay, well, what is the net charge? Well, Q net inside the surface. We don't care about all this stuff outside the surface, right? It's just the stuff that's inside, that's enclosed in the volume that the surface encloses, is Q1 minus Q2 minus Q5, where I'm including the sign of the charge here. So then Q2 is, this is going to be a magnitude, I could illustrate that like this. All right, so those are just magnitudes, but I'm including the signs here, negatives. So then I is going to be equal to Q1 minus Q2 minus Q5 over epsilon naught. All right, so why don't you try these right here. Got two examples. You guys hit pause and try these. All right, welcome back. Let's check your work. So here there's one positive charge that is enclosed by this surface. So I'm going to put that in here. 2e minus 6 coulombs over, and epsilon naught is 8.85 e minus 12 coulombs squared per Newton meter squared. So the net flux here is going to be 2.26 times 10 to the 5 coulombs, Newton meter squared per coulombs. Here we go. Okay. All right, and then so the units on this are the units of the electric field, newtons per coulomb, times the area, meters squared. So those are the units for electric flux. All right, so here on the right one, I've got all these charges, but the surface is this gray kind of blob here. So I want to look inside that, and I have the net charge in the enclosed surface is 6 minus 4 minus 1, which is 1 microcoulomb. So that's what's going to go in my equation. And whenever I crunch these numbers, I got 1.13 times 10 to the 5 newtons meter squared per coulomb. All right. So this is Gauss's law. You've got some homework to kind of reinforce some of these concepts. Your textbook also talks a little bit about Gauss's law in the context of some different symmetries. We're gonna kind of skip over that, but if you want to, you can take a look at those. It essentially looks at cylindrical symmetry. We already looked at the spherical symmetry, but the easiest math occurs when the Gaussian surface aligns with the symmetry of the electric field, right? And that's because when it aligns with the symmetry of the electric field, the angles, thetas, are all 0. All right, I will see you guys on Wednesday.